Okay, so let's get started. Okay, so this is MSE 498. So if anyone's not in the class, if you could please vacate your computers. We do need all the computers for the students in the class. So thank you for that. Sign-up sheet. Okay, so just to orient ourselves on the syllabus. So we're now on a rainy October 9th. And so we're a little bit ahead of the game. And so today we're going to be finishing up the walkthrough and start getting into the project. And so we should get the walkthrough done probably within the first 20 minutes, half an hour, and then we can start working on our project together. The project is up on Compass, so if you go to Compass and navigate to Project, you will see that the LAMP folder is now active, and so that's immediately available for you to start working on. Okay, and so where did we finish up last time? So if you remember, we were working through the input file that was going to allow us to build this system, which was basically sort of just a crystalline block of aluminum in which we had cut a little notch. And so this notch is going to be semi-infinite in this direction, and we're finite in Z and X. And then we said we're going to define some atom groups. So we have this special group of atoms at the top wall, this other group of atoms at the bottom wall, that we're going to start pulling on to try and cause the crack to propagate. So this is simulating a material under tension with an exterior crack in it. And all these atoms are going to evolve normally according to Newton's equations of motion. And we're going to see the crack ultimately propagate through the material. And so this input file was a little bit more complicated than the previous one. Probably the most complicated thing, at least from my perspective, was actually setting up the geometry. So if we go back one slide, we had all this sort of crazy stuff where we were basically just measuring the block and then determining where we're going to define the top wall and the bottom wall. So it looks kind of esoteric when you see it, but it's nothing more than sort of just geometry. It's just saying, where should I place my boundaries to put the top wall and the bottom wall, and then defining groups such that I can define the boundary atoms and the mobile atoms, which are going to be in the bulk of the material. And so if you do have any questions remaining about that stuff, please let me know. You are going to be doing a little more geometry stuff in your project, so it's sort of important to have a reasonable handle on what's happening here. Okay, and then we're moving forward. We said, okay, we're going to reset our timer. We're going to set up our time step. We're not going to be too greedy, so we're going to pick 2 femtoseconds. Why is this femtoseconds? Because it's 0.002 picoseconds, because picoseconds are the natural units of the metals choice that we made at the top. We initialized the velocity of the atoms in the mobile region from a Maxwell-Boltzmann distribution at 300 Kelvin. Why? Because we don't want to shock our system when we start integrating Newton's equations of motion. We want to give the atoms some initial velocity so they're at approximately the temperature we care about. And conversely, we set the boundary atoms to 0 velocity because they're not going to evolve according to Newton's equations of motion. They're just going to sit there and provide handles for us to pull on the system. And so we grab the wall. The wall atoms do not evolve according to Newton's equations of motion, but they do interact with the rest of the atoms in the system. So they are interacting and holding together with the mobile atoms, and so ultimately when we pull on them, the system is going to propagate the crack. Okay, and so then we said, let's apply our thermostat and our barostat through this fix. We tag the fix with ID 1, and we apply it only to the mobile atoms. That's very important. Previously, this has been all, because all atoms in the system. Here, it's only the mobile guys. It's going to be an NPC, because we have a thermostat and a barostat. We said the temperature is going to start at 300, finish at 300, and have this damping constant of 1 picosecond. The pressures are going to be coupled only in Y because we're finite in X and Z, so we don't want our atoms to spin off into space. We only want pressure coupling in the Y dimension. And the pressure is going to start with a target of 0 bar, finish with a target of 0 bar, and have a damping constant of 1 picosecond. And then we just have this drag coefficient that makes the thermostat and the barostat a little bit more sort of sluggish or relaxed so they don't go crazy and destabilize. So this is a standard choice. You just pick drag equal to 1. If you picked the drag equal to 0, you would still be fine. So don't worry too much about this term. Okay, then we just have some instrumentation. So all of these guys down here in the double quotation marks are internal LAMP variables. You can figure out what variables are available by looking in the documentation. And then we use this nice idiom where we assign these variables to a user-defined thing, in this case S1 through S10. And then we can print them all out to the screen. And so, actually, we're printing them to a file. And so we define this fix called writer. It's going to operate over all atoms. It's going to print every 250 time steps, and it's going to print all this stuff. And so S1 through S10 are things that we define. The time, the dimensions of our system in X, Y, and Z, the volume, the pressure, the potential energy, the kinetic energy, the total energy, and the temperature. And we're going to write it to the file al_eq.txt, and actually we're going to analyze this file afterwards. We're going to do a postmortem on this file, make some plots, and check that our system is behaving in the way that we expect. Okay, then we defined a thermostat, which prints stuff to the screen. So we said thermo every 500 time steps. I want you to print the following to the screen. Thermo_style is our keyword. It's going to be a custom. There are some built-in ones you can use, but I almost invariably use custom because I want to understand different things for different systems. And we said I want you to print the step, the time, the CPU time remaining, system dimensions, pressure, potential energy, and temperature. That's stuff I'm interested in. I want to see during runtime. Finally, we said, okay, I'm dumping this information to this file al_eq.txt, but I also want to dump the atomic coordinates at every time step so I can visualize my atomic simulation trajectory. And so I'm going to use the dump command. I'm going to tag it with the number 1. It's going to operate on all the atoms in the system, and the dump style is going to be atom. That's a format that Ovito recognizes very simply. We're going to write every 250 time steps, and we're going to call the file this, dump.eq.lamptraj. Okay, so just one word of warning. Don't get too greedy with how frequently you dump, because these files can get really big really quick. And so if you dump every time step, you can max out your home directory in a matter of minutes. And so just be a little bit careful of that. Always err on the side of less frequent dumps until you have a good handle on how big this file is going to be. If your lamps run terminates halfway through and you don't know what went wrong, it doesn't actually even give you any errors, probably you've run out of disk space. And so then check your home directory has not been maxed out. So that's just a good technical thing to check. Okay, so all this sort of nightmare setup, it's really confusing. We don't know what's going on. We'll get there. We'll do the walkthrough. We'll do the project. This is when we run the Verlet algorithm. So this is all set up. This is actually doing molecular dynamics. So this says run. If you look up the keyword run in documentation, will be integrate Newton's equation of motion using the Verlet algorithm plus any fixes you may have defined. So this fix is going to happen at every time step also, to make sure we're not just doing F equals MA, but we're also controlling the temperature and the pressure. Okay, then we said we're actually going to do another run in just 1 second. This was all just equilibration, and so we want to unfix and undump our tags fix and dump so that we close out those files and we don't overwrite them by mistake later. So that was that unfix, undump. And then we just saved this variable. So we define this variable TMP is equal to the instantaneous value of LZ. And so we store the instantaneous value of LZ into this variable TMP. So that says, what is the Z dimension of my system at the end of my equilibration run? We then take TMP, access its value, and store it in this variable LZ naught. So why do we use this sort of strange idiom? Why can't we just store LZ directly in LZ naught? The reason is because if we did that directly, so our call would look like variable LZ naught equal LZ. The problem with this is that LZ is going to continue to change. We're about to do a new molecular dynamics run where we actually apply tension to the walls. This is going to continue to evolve because the system is going to change. And so when we try and access this variable, we will no longer have the quantity we think we have, which was the extent of the system at the end of the equilibration run. So we have to do this sort of two-step process where we store LZ into temp, so then we get its instantaneous value, and then we dereference temp and store it into big LZ naught. And so that makes sure that we have a single value that's no longer going to change in time. So it's a little bit strange. So do folks pretty much get that? Is there any questions about that? Yeah. Say that again. We set in the green block. Yeah, so in the green block, S4 is LZ. That's right. You could have. That's right. Yeah, because you set S4 equals LZ. You could have done that. Yeah. Very nice point. Okay, so this is sort of confusing, and so if people still don't understand that, ask me when you're doing the walkthrough. Okay, so are there any questions? This is all sort of still recap. We did this last time. Are there any questions on any of this stuff? Okay, so we had one more page of the input file, and then we're ready to go. So this is a little bit simpler, because you've seen a lot of this before. So we've equilibrated our system. We were doing Verlet algorithm for the mobile atoms. We had these walls, which we were saying we're just going to keep the velocity equal to 0, because they're not going to do anything. And so the picture we have in our head is that we have the top wall, we have the bottom wall, we have all the mobile atoms, they're all jiggling around, they're all moving as you would expect atoms to move at a finite temperature. These atoms are all frozen. We're not updating their positions or their velocities according to the Verlet algorithm, but crucially, they still interact with their friends in the mobile region. And so they're still sticking together through their interatomic potentials. So that means when we tug on the walls, we're also going to tug on the mobile atoms. And so there's sort of a strange aphysicality to this. You could never do this in an experiment. You could absolutely do it in a simulation where they're frozen, but they're still interacting. Okay, so just an important concept to keep in mind as we're progressing with this. Okay, so we've equilibrated our system. We know that when we set it up, we weren't going to be at thermal equilibrium, so we let it run for a little while to equilibrate it. And when we analyze our output from the equilibration simulation, we'll check that all our quantities are stationary in time. So our temperatures start just fluctuating around the value that we want, 300 Kelvin, and the pressures start fluctuating around the value we want, 0 bar. And so when those have equilibrated, we're ready to actually start applying our forces to the system and rip it apart and watch the crack propagate. Okay, and so if you don't know how long you have to run, typically you would do an equilibration run in one input file. You would do it, see if you did long enough, and then you would be happy, and then you would write a brand new input file where you actually yank on the walls and propagate the crack. I know that the equilibration is going to be long enough, and so we've written a single combined input file where we do an equilibration run, then immediately afterwards we do a deformation run. So if you don't know in advance, typically you want to split those two files up. But just to make things concise, we're just doing them serially right here. Okay, so this is just right below equilibration. So we've just finished storing our LZ naught, and then we say, okay, labs, we're happy our system is equilibrated. We'll prove that in a second. So let's reset our timer. Let's respecify our time steps. This is exactly the same. You may, for some reason, want it to be different, and so I just provide you that option here. Then we're doing something slightly well, we've actually seen this before, and so we're fixing the mobile atoms with an MPT, barostat thermostat, all the same values as before. But now we're doing something different with the walls. So before, we just left the walls stationary. So if we go back one slide, the fix we were applying to the walls was just to say, let's set all the boundary atoms with 0x, 0y, and 0z velocity. So they're not doing anything. They're just hanging out. When we're actually deforming the system, we want to pull on the walls. And so we have to define the following fix. And so we could pull on the top and the bottom wall simultaneously, pull them together, or we could just leave one of the walls fixed and pull on the other. And so we're going to choose the latter path. We're going to define this variable big VZ is equal to 1.0, and then we're going to apply this new fix, which we're going to tag with the number 2, to the top wall. And so you can look up all the possible options for fix, and one of them is move. We're going to move with a special variable where we have null, 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 v, v, z. So what the heck's happening here? This says, what do you want the x, y, and z coordinates to be? We don't care about that. They just are what they are. And what do you want the x, y, and z velocities to be? We don't care about the x velocity, the y velocity. We do want to apply a z velocity. And so the nulls just tell lamps, just whatever the current things are, we're happy. But we do want to apply a velocity in v. And this is our variable big VZ, so we reference it as little v underscore VZ. And this means that every time step, we go into the top wall atom, and we say, okay, top wall atoms, you can do whatever you like, but I want your Z velocity to be 1.0 in the units of metal, which is going to be angstroms per picosecond. And so it means we're forcing the top wall to move up at a constant velocity, and that's going to pull our system apart. So is everybody okay with that? We could have done something different. We could have said, let's move the top wall with a v velocity of 1/2 Vz, so they move up with 1/2 Vz, and we could move the bottom wall down with a velocity of negative 1/2 Vz. That would give us exactly the same phenomenology. So it's your choice. Okay, so that's kind of important, because that's kind of one of the ways that we're introducing sort of a new concept here, which is an artificial force on our system. So any questions about that? Yeah. MPT stands for the ensemble that you want to operate in. So when we talked about ensembles back in the theory slide, we said that experimentally you typically operate in the MPT ensemble, which means you have a fixed number of particles, a fixed pressure, and a fixed temperature. And so if we want to fix our temperature and our pressure, we want to attach a thermostat and a barostat. And so the keyword for doing that is NPT. So if you look up fix in the LAMP documentation, you will see you can pick anything you like. You could pick NVT, you could pick NVE, and so depending on what experimental conditions you want to simulate, fixed temperature, fixed energy, fixed pressure, fixed volume, you pick the correct fix. Does that make sense? Okay. Okay, so what do we do now? We're moving into the green block, and so we've seen all of this stuff before. And so we're going to define a thermo. So every 500 steps, we're going to print some stuff to the screen. What are we going to print? Again, we're going to define a custom thermo style. And so we have all these usual suspects, stat, CPU remain, the pressure in X, Y, and Z, which are the diagonal terms of the pressure tensor. And then we have the off-diagonal terms, which give you sort of the shears, so the shear pressures or the shear strains, potential energy and temperature. And then this new variable, V underscore strain. So we know it's a user-defined variable because it starts with V underscore. So somewhere we must have defined strain, and we define it right above. Variable strain is equal to the following. And so what are we actually doing here? We're defining a strain. And so we're saying our strain, which is basically the fractional elongation of the system in the Z dimension. So how much more elongated have I become relative to my original position? Definition of strain is the velocity by which we're accelerating the top, we're moving the top wall, so the constant velocity of the top wall, times the number of elapsed steps times the time step, so that's going to give a distance. And so that's telling us, okay, we start at t equals 0 with the wall right here. We're moving up with a constant velocity vz, and so at a later time, t is equal to t1, we've moved up how far? Well, it's just this distance is Vz times delta t. And so that tells you how far the top wall has moved up. And delta t is the number of steps you took times the time step per step. So it's number of elapsed steps times 2 femtoseconds, because that's how long each of our time steps are. So that tells us how far the wall has moved, and then we defined our strain is equal to this quantity, Vz times delta t over LZ naught, because that's your original size of the system. And so that's the original length of the system in the Z dimension. So that's going to be our strain. So if you're not a material scientist, look up strain on Wikipedia, look up stress and strain, and you'll see strain is defined nothing more than this. So the percentage elongation of the system, basically. Okay, and so we're defining that variable, and then we're using this variable to print out to our screen every 500 time steps. And so this is good because this is a variable we're interested in, because we want to check that the system is actually getting longer as a function of time. If this is not changing, we know something is wrong in our simulation. So it's a little bit of a stretch, but this is sort of like, I think I referenced the Matrix before, and so I feel bad doing it again. But it's like when you're watching the Matrix, you can, well, not you, but people watch the Matrix, you can see what's happening. You can look at all the characters moving on the screen and understand what's happening in the system. It's the same idea with the thermo here, that by printing stuff to the screen during runtime, you're basically instrumenting your system. And so you can watch the text, scroll down your terminal, and check if something's going wrong, or check if it's happening as expected. So why is that useful? If you're doing a really long run that's going to run overnight, you probably want to spend 5 minutes before you go home in the evening checking that it probably looks like it's going to be okay, so when you come back in the morning, you haven't just generated a bunch of junk. So instrumentation is vital. Okay, and so then we have a little more instrumentation that we're actually going to dump to a file. So this goes to the screen. We're defining a fix that's going to go to a file. And so we're interested in all of these variables. The strain we just talked about, the pressure in the X direction, Y direction, Z direction, and then the off-diagonal terms of the pressure tensors, so like the shears, if you like. And we're going to define a fix. We're going to call it writer. You could call it whatever you want. You could give it a number. You could give it a different name. You could give it your cat's name. It doesn't matter. You just call it something. It's going to refer to all atoms in the system. We're going to print every 100 time steps. We're going to print all this stuff, which we just defined, P1 through P7, which we defined up here. So of course you could refer to these directly in line, but it just provides you a little more flexibility if you define them up here and then you call them by their new names a little bit later on. I'm going to write it to this file, al_crack.txt, and we don't want it to go to the screen because we already have our thermal information going to the screen. So we have a bunch of output in this file. Basically it's just going to be a file of columns of data where each column is P1 through P7, and we're going to very nicely be able to import that into MATLAB and make some nice plots very efficiently. Okay, then we also want to have our trajectory as usual, so we're going to dump, we're going to tag it with the number 1, the entire system, all atoms, format atom, every 500 time steps to this file, dump.crack.lampstrash. So we've seen that before. Okay, so we're actually going to define a new dump also. So we're going to define this dump, we're going to tag it with the number 2, it's going to refer to all atoms in the system, but this time the format is going to be CFG. So this format was atom, the new format is CFG. And so this is a different format that's also recognized by Ovito, and it provides a little more customability. And so we're going to dump every 500 time steps. We're going to dump it to this file called dump.crack_*.cfg, where the asterisk gets replaced by the current step number. So at step 500, you're going to generate a file called dump.crack_500.cfg. At step 1000, you're going to generate a file called dump.crack_1000.cfg. So for every time point, you get a separate file. That's very different from when you dump format atom, where you dump it all to the same file. So it's just a different way of doing things. Okay, and then you can actually customize what's going to go into this file, or each of these files at each time point. So we are going to dump the mass of our atoms, the type of the atoms, they're all going to be aluminum, the x's, the y's, and the z's, which are the coordinates of our atoms, the force in the x direction, the y direction, and the z direction, the value of our central symmetry parameter. And so if you look back up to the top of the input file, we defined a variable called csim, which we talked about last time, which was basically how close am I to the perfect FCC crystal locally. If I tag an atom and look around that atom, how close is it to a perfect crystal? And the energy, so C_energy. So this was the other compute that we defined, which was basically the energy of each atom. And then we'd also define the atom stress. And so in 1, 2, 3, 4, 5, 6, these are the local stresses experienced by the atom. And so I think this one is a built-in variable, so we didn't have to define it. So you can look it up in the documentation, and you will find that element 1 of atom stress corresponds to its stress in the x direction. Element 2 corresponds to stress in the y direction. Element 3 corresponds to stress in the z direction. Element 4 corresponds to stress in xy, so the shear stress. Element 5 is xz, so another shear stress, and 6 is yz. So basically for every atom, we have this really, really detailed accounting of what are the atomic level stresses experienced by the atom. So this is sort of remarkable. This is something you could never get experimentally. And we're going to use this when we visualize our simulation trajectory to watch the evolution of stresses on an atom-by-atom basis as the crack is going to propagate through the system. And so as we start tugging on the walls, you're going to see the atoms near the crack tip are going to experience the highest stress in the z direction, and that's going to cause the system to rip apart. Okay, so that's another level of instrumentation. And this final line, dump modify, so we're modifying the dumps that we tagged with number 2, and we're just saying, okay, I want you to say all the elements are going to be aluminum. So that might be important because if you load into visualization suite, in our case Ovito, it may color elements by different colors based on their identity. And so in this case, we're just making sure that how we dump to this file tags everything as aluminum. So that can be useful for visualization. If you don't do that, your data is not going to change, but the color that you see in a visualization may change. Okay, so any questions on that stuff? Yeah.
I just kind of had a question about maybe instrumentation. So because we have constant velocity, does that mean no matter what I would try to do, that not even for breaking, like increase radius and curvature, something is going to break because it's always going to be separated?
That's right. So eventually it is going to break. So you can pick sort of 2 different ways to cause the crack to propagate. So one might be to apply a fixed force. And if you're below the crack propagation threshold, the crack is not going to propagate. If you're above, it is going to propagate. So maybe you could do a bunch of separate simulations, each at a different value of the force. And you could see at what value of force do you need for the crack to move. Alternatively, you could do a single simulation where the force is going to be a ramp. And so you start with 0 force, and you start ramping up the force, and eventually it's going to tear. Another way to do it is to actually not control the strain, which is basically not to control the stress, which is what you're doing when you're applying a force, but to control the strain. And so if we think about our stress-strain curve, So this is our strain and this is our stress. At least in the linear regime, it's going to look something like this. So you can either control the stress and measure the strain, or you can control the strain and measure the stress. And so we're doing the latter in this case. We're controlling the strain and we're going to measure the stress. Yeah, good point. Okay, so we're very close to being done. We run the MV simulation. So we're doing relay algorithm for 15,000 time steps. So our simulation is going to be 15,000 steps times 2 femtoseconds long, which is going to be 30 picoseconds. And then after we get done, we're going to unfix and undump just to clean up after ourselves. Again, not necessary, but good practice to make sure you close out all of your fixes and your dumps. And so, okay, there's kind of a lot going on here. And so the best way to learn it is learn it by doing. And so let's run the code. So one last thing before you go ahead and do this, I would recommend, because these workstations are not as fast as I had anticipated, that we actually reduce our system size so we're not just waiting forever for our system to run. And so what I'm recommending, and there is a typo in the notes, I reposted them, but I omitted this 0, I believe. It's fixed now. But go to your input file where we're defining the size of our simulation, basically, where we're defining region, whole, block, and I think it reads like 040, 04, 040. So I'm recommending you change it to the following, just so your simulation is smaller, and so therefore it runs quicker. Okay, so you don't have to do that if you don't want, but it's going to take sort of 10 or 15 minutes for your simulation to run. If you reduce this, it should cut it down to sort of 5 minutes. So go ahead and make that modification, and then let's run our simulation. Okay, so I'm going to change my region size. Okay, now I'm going to run. Okay, so we're running, and so you can see that this is all the setup that's printing to the screen. This is also being saved in a log file simultaneously, so you will have it for posterity. And this is our instrumentation for our equilibration blocks. This is the thermoprint, the custom thermoprint that we defined. And so it's printing the steps, the time, CPU time elapsed, CPU time remaining, system dimensions, pressure, potential energy, and temperature. And so we can reach through this and see if things are progressing as we expected. So the steps are going up, which is good. CPU time elapsed and remaining are relatively going up and down. So we can see we have about 96 CPU seconds left. Then we have our system dimensions, and so they should not be changing too much. We're sort of equilibrating. So if they're going crazy, you need to be worried. The pressure started pretty low, sort of negative 2,000 bar, but is sort of then moving up, and now is starting to fluctuate around 0. And then the temperature is sort of getting there towards 300 Kelvin. And so, yeah, the temperature is over on this side. Okay, so we're up at sort of 280 Kelvin now, and so we're moving towards our desired temperature. So just a rule of thumb, you should expect to see temperature fluctuations off the order, this is very dependent on system size, but off the order sort of 10, 20, 30 Kelvin. Fluctuating around the value you're targeting, which in our case is 300 Kelvin. Pressure tends to fluctuate a lot. And so on average, it should be the value you want. So 0 bar in this case, so 0 net pressure. But you could see fluctuations of several hundred bar either side of that. That's nothing to worry about. It's basically a function of the second moment of the distribution of your pressure, which is determined by the compressibility of your system. And for most systems, we care about the compressibility is such that that second moment is large. And so we see fluctuations of several hundred bar. It's nothing to worry about. As you increase your system size, those fluctuations start to narrow. And in the thermodynamic limits, So the experience of everyday objects that we're familiar with, when you have Avogadro's number of atoms or molecules, the width of that Gaussian is so small that basically we measure a single pressure with essentially no fluctuations. When we're simulating things that start on the microscopic scale, fluctuations are just a fact of life. Okay, so has everybody got that running? Has everybody not got it running? Yes.
Not right.
Okay, so it's angry or your region command. And so let's look in your, yeah, so hit that command again. So VI. Yeah. Yes, so this was what I was saying, this version of the notes, there was an error. And so if you download the new version, it's fixed. It should be 015, 02, 015. No, there's a missing 0. So this is the extent in X, 0 to 15 angstrom. This is meant to be the extent in Y, which should be 0 to 2 angstrom.
Okay.
And this is the extent in Z, which should be 0 to 15. So you're just missing a 0. Yeah, that was my fault from the old version of the notes. So if you stick a 0 between the 15 and the 2, you should be good. Yeah, that looks right. All right, we're good. Yeah.
So I noticed that if I didn't bring my screen to the big size, it kind of switches all things together.
Yeah.
So, but even if after I readjust the package doesn't go back.
So you need to email the developers of this version of Linux and tell them that you're unhappy with how they've designed their terminal.
And also like for the black code, is it so they didn't pair it up again and didn't create the column?
Yeah, so the terminal isn't a great place to do nice formatting.
Oh.
Yeah, so there are ways of doing it, but typically people don't worry about it. I mean, the text is going to look ugly whatever you do, and so people tend not to worry about sort of aligning.
Oh, okay.
Yeah.
I know, of course, it's big enough for it. Because otherwise, I noticed that.
It's going to wrap, that's right.
Like,
Yeah.
Like the 60 point something kind of views over here.
Yeah.
And you're missing all the data.
That's right.
And even after, I think it doesn't make it.
Yeah. So yeah, I mean, this line has like wrapped around, so all the data is there. It's just not in its nice column form.
Could you somehow use the function to retrieve the data?
Well, actually, you don't care about this, how it looks on the terminal, because exactly the same information is stored in the log file.
Oh, so they just access.
So you just access the log file. Yeah. But this is a good point actually, because maybe you don't want to print so many things to your screen that it causes it to wrap. So maybe you want to be a little bit parsimonious with how many variables you print to the screen.
Oh, okay.
So
when we're doing the project.
yeah, so just for your own convenience, maybe that's the consideration you want to worry about.
Speed-wise.
Speed-wise.
It's just exactly.
Yeah, unless you really go crazy and ask it to print so many things, it's actually burning CPU cycles to do the print to screen.
Oh.
But that's usually a very minor consequence. Okay. Anyone else having trouble running? Great. Terrific. So where are folks at? Are folks on the deformation yet? So the equilibration is run. The deformation ran. Very good. Is anyone still waiting for their simulation to finish? Okay, terrific. So mine is taking longer than everyone else's, which is concerning. But what we're going to do now is we're going to look at what is being produced. So let me move this out of the way. And so you should see something called log.lamps. And so let's just visualize this in a text editor. Okay, so this should look familiar. This is your input file just being reproduced in the log file. And then if we scroll down, you will then see all of the information that was printed to the screen has also been stored in this log file, and so that we can analyze this log file at a later time, even after we close our terminal. And so all the information is there about the run. That's the equilibration run. This gives us some CPU statistics. So let's take a look at our neighbors. we don't have any dangerous builds, so that's good. We're happy with that. And then we stored our final variable, and so we get our final value extent of the system in the z dimension. Okay, and then we ran into the deformation block, and so then we're executing that. This is the simulation. And again, we don't have any dangerous builds, and then we print it all done. And so all the stuff in the screen plus your input file is stored in the log file. And so it provides a sort of very nice accounting of what you told the system to do and what actually occurred. So it's a trace for you of what actually went down. Okay, what else do we have? We have our dump.eq.lamps trash, and so that's what we can use to visualize the simulation, the simulation trajectory for the equilibration portion. We have, I guess we could look at this. It's going to be in the format we previously discussed. So it's in this format. It's just a standard format that Ovito is going to recognize. It's basically a listing of all the atoms in the system. They're tagged. They're all type 1 because we only have a single atom type. They're all aluminum. And their coordinates. And so that's for time step 0. If you scroll down, you will get the same for time step 1. Well, however many times however frequently you decided you wanted to print. You'll have 1 for every frame, basically. Okay, so we're going to visualize that in just a second. And then we also have aleq.txt, which is this text file that we made a fix called writer that was going to print through the text file. And so this is all the data line by line that we asked to be printed to this text file. So if we look back in our input file, we can find out exactly what that was. Okay, so equilibration run, fix writer is going to print time, Lx, Ly, Lz, volume pressure, potential energy, kinetic energy, total energy, and temperature. And so line by line, that's exactly what's being printed out here. So we're going to analyze this with MATLAB in just 1 second. So what else do we have? We should also have the lamp trajectory from the deformation run, which we called crack. And also this other information file, line by line, that we asked to be printed as a function of time for the deformation run. So again, we're going to analyze that. Okay, so does everybody have all those files? Those have all been generated successfully. Okay, terrific. So now let's study them. Okay, so let's close this out. Close this out. Okay, this is the run I actually just did. Okay, so the way we're going to analyze them is I've tried to make this very easy. I've written a MATLAB function to do it for us. And so basically this MATLAB function is going to do a whole bunch of the things that we learned to do in our MATLAB block. And so we provide it an argument, which is the name of the txt file that we want to analyze. It knows exactly what format this is going to be in because I wrote the script to interface nicely with the LAMP input file. So this is going to generate this in a particular format that the script is going to accept. It's going to import all the data in that file, and it's basically just going to make some nice plots for us. And so let's take a quick look at the script. I don't really want to get into too much detail because we've seen all of the commands before, but it should provide a useful template for you to generate similar scripts for your project. Okay, so this is the MATLAB M file, and so it's expecting a function name, the input. We're going to import the data. It's going to load it as a bunch of columns. We're going to pull out each column and give it the name corresponding to a particular variable we cared about: time, side length, volume, pressures, kinetic energy, temperature, etc. We're going to define some plotting variables, and then we're just going to make a bunch of plots. And so let's pick one randomly, this one. So what are we actually going to plot here? We're going to plot the side length of the box as a function of time, and then we just have some nice plotting options. So it's going to be a line with points as circles. It's going to be in color red. We're going to give it some nice axes and change the size of the font, etc. So we're just making some plots and customizing them. So very nice and quick way to quickly generate plots from your data. And so now we don't have to just rely on staring at text files. We can actually make plots as a function of time and see how our system is evolving. So let's just run this. So if you boot MATLAB, and navigate to your directory holding all of your files and hit the following command. It will load aleq.txt and make a bunch of nice plots for us, which will look something like this. Okay, so has everyone been able to generate these plots? Has anyone not been able to generate those plots? Okay, terrific. So what do we want to see here? So we're analyzing the equilibration portion of our run. And so we want to equilibrate in temperature, pressure, and energy. We want to make sure those are all no longer changing in time, because then we can be sure when we actually apply our deformation that we're applying it to an equilibrated system. Okay, and so let's look. Everything is x-axis is in time/picosecond, so always make sure you label your axes with the units, so picoseconds. And this is the box side length in y. This is the pressure in the z dimension, temperature, and the three energies, kinetic, potential, and total. And so we see that the box actually started a little bit too small, the pressure is a little bit too high, and so then it equilibrated very quickly to around 8.1 angstroms, and it's just fluctuating around that value. So the barostat is at every instant saying, what is the pressure? If it's too high, I'm going to make the box a little bit bigger. If it's too low, I'm going to make the box a little bit smaller. And so that's exactly what's being seen here. And similarly here, the pressures start fluctuating around 0 bar. Fluctuations are large. Like I said, that's okay. How does the temperature look? Although we did initialize with a Maxwell-Boltzmann distribution, it turned out when we started up the Verlet algorithm, the way we initialized the velocities was such that there was a temperature only of about 150 Kelvin. And so the thermostat had to do some work to heat up the system and bring it to equilibrium at 300 Kelvin. This is now flat. We're happy. We're at equilibrium. And all the energies are basically flat all the way through the run. If you zoomed in here, you would probably see some larger fluctuations, but everything is now pretty happy. So if we had run too short, so imagine we'd only done a 10 picosecond run, this would have a gradient in the side length, there would be a gradient in the temperature, and we would know, okay, we've not run long enough. We're not at equilibrium. We're not happy that we've equilibrated. So it's always a good check to make sure all these things are steady. So one minor caveat, we can never be sure that on much, much longer timescales, something else is not going to happen. So we're equilibrated on the time scale of tens of picoseconds. If we had done a run for a microsecond, something else might have happened. We just don't have the computational horsepower to do that, and so the statement that we make is that we're equilibrated on the simulation time scale, which is tens of picoseconds. That's the best that we can do. Okay, so now we're equilibrated. We're pretty happy. So let's go back to the slides. So these are the plots just in the slides. Let's do a similar thing to analyze the data that came from the deformation run. And so let's run al-crack, and then we're analyzing this file that was spat out by our lamps run. So now we've equilibrated. To our equilibrated system, we're going to tug on the top wall, and we're going to apply a strain. And so we're progressively moving up in strain, and we're going to analyze the stress response of the system. And so if we run this, you should see some plots that look like this. And so what are we seeing here? We're plotting strain on the x-axis in both of these plots, and on the y-axis, we're plotting stress, which typically goes by the Greek symbol tau in gigapascals. Why is it gigapascals? Because we know exactly what the units are going to be that come out of lamps, and we can process them and turn them into gigapascals. So that happens under the hood of the MATLAB code. Okay, so let's look at the plot on the left. And so we're plotting the diagonal components of the pressure tensor, so the pressure in x, y, and z. And so what's happening to the x and the y pressure? Not very much. And so we're applying the strain to the z dimension, and in x and y, essentially nothing is happening. And so those are flat. So that's in line with our intuition. The z pressure, or the z stress, I should say more precisely, is going crazy. And so we're applying the strain. The stress response looks like this. And so we're trying to strain the system, we're pulling it, pulling it, pulling it. The atoms of the system in response are trying to tug the system back together. And so we see this linear regime, which is the Hookean response of the system. You tug it, it responds. Then eventually it breaks. And so at this point, you see this release of stress. And so if you're a material scientist, you'll immediately recognize this as something sort of catastrophic has happened. There's this turnover in the stress. the pressure has been relieved, and so something in the system has sort of relaxed. And obviously we anticipated this is going to be the crack propagating. And so at this point we've reached this threshold stress and the system is sort of torn apart. And so to John's question, we could have instead controlled the stress. And so we could have controlled the stress of the system. Instead of applying a constant velocity to the wall, we could have applied a ramp in the force, and we would have basically been controlling this axis, and then we could have measured the strain. We could have said, well, actually, for this given stress, how much of a strain, how much of a deformation have I seen? So it's really your choice. Okay, then we actually look at the off-diagonal components. So these are the shear stresses in the system, and these are all basically flat as well. So look at the axes on these two plots. They're very different. These guys, the shear in XY, XZ, and YZ are basically just fluctuating around 0, which is in line with our intuition. There shouldn't be any shear stresses. There should only really be normal stresses. Okay, so it looks like what has happened is that we've strained the system to such a degree that the crack has propagated. So how are we actually going to check that that is true? We're going to visualize it. So let's boot Ovito, and let's actually watch this crack propagate. Okay, so let me close out this. We will just type Ovito into the terminal, and Ovito should pop up. Okay, and then you go to open up your file. So if you go to the top left and click this button, you will then navigate to the output file from your run, which is going to be, the first one you can look at is dump.eq.lamptraj, so nothing too exciting should happen with this. So let's load it. Let's tell Ovito that the file contains multiple time steps. So in the bottom right, click this button, and then you should be able to play your movie. And so you see the atoms are just sort of jiggling around. If you look very carefully, you will see the top wall and the bottom wall are fixed because we said do not integrate Newton's equation of motion for the top wall and the bottom wall. Just pin their velocities to 0. The ones in the middle are all moving according to classical mechanics. And so we're figuring out how they're talking to all of their neighbors through the EM potential function. And then they're all just jiggling around and equilibrating to 300 Kelvin and 0 bar. Does everyone manage to visualize that okay? Okay, so we can watch it run. It's just going to loop round and round. So once it hits sort of 60 frames, it's going to shoot back to the beginning. Okay, so let's open the crack run. So I'm just going to do exactly the same thing. Open the file. I'm going to say replace the selected because I just want to load the new data. Tell Ovito that the file contains multiple time steps. And you can watch your system tear apart. So that is going to be dump.crack.lamptraj. So it was the second dump file that we wrote during the deformation block. So is everyone able to see that? You find it? Okay, good. Cool, looks great. All right, terrific. So it looks like what is happening is what we expected, basically. So let's go a little bit further and do some more visualization. So the other files we can visualize are these CFG files. So if we go back to our input file, we go down to the deformation block, yeah, just a quick reminder. We reminded that whenever we start a line with a hash, or the pound symbol, it means it's a comment. And so do try and comment your input files liberally so that they're sort of human readable. And so you can make different blocks, you can give clues as to what you're actually specifying, et cetera, et cetera. So it makes it very easy to find the deformation block, go down to look for dumping trajectory. And this was the second dump command that we called. And so in this case, it's going to be a different format. It's CFG, and we said we're going to get one file for every time step, which is exactly what we're seeing here. And we've asked for the atom mass, type, and some bunch of extra information. So we've got the mass of the atom, the type of the atom, the X's, the Y's, the Z's. Typically, whenever you dump a CFG, you always have these 5 things, plus any extra stuff you care about. And the extra stuff we care about are forces, central symmetry parameters, energies, and stresses. And so that information is not contained in this dump file. It only dumps the atom coordinates. So if you want to make a trajectory containing extra information, you need to use the CFG file version. And so that's very flexible. We can dump all this extra information. So let's use those for some visualizations. So let's go back to Ovito. And let's open up dump.crack_0.cfg. It's the first one in our trajectory. So let's open that guy. Let's replace the selected. So right now the trajectory looks identical. So we have no new information as yet compared to the previous file that we loaded, because all we're seeing here, the atoms start moving as a function of time. But what's very nice about this file format is it contains all this extra information. So if you look here, the best way to think of Ovito is as a pipeline. And so down here you load the file. And so these are different files that's being loaded, and then the pipeline moves up. So I don't know why it moves up. I think it should move down, but that's just the way it was written. And so you load the file, and then we're displaying the file. And so by default, we're displaying the simulation cell and the particles. The particles are obviously red. Simulation cell is that sort of white box. Between the input and the display, you can add modifications to visualize different things. So if you click on your input and then go up to here where it says add modification, you can do a bunch of different stuff. And so maybe the first thing we would like to do is, let's color code the particles. So if you go down to coloring and pick color coding, you can then go down to the bottom window and you can see how you would like to color code the particles. Okay, so what does our pipeline look like now? We're loading the data. We now go through a color coding operation, and then we display the data. Think about the pipeline moving up. Does everyone manage to do that? Okay, so by default, they're color coded according to mass, which is not very interesting because they're all aluminum, so they all have the same mass. But look here. So when we click on property, we have all the extra properties that we asked LAMP to dump for us. And so these properties do not exist in that previous atom dump file. They only exist in this new CFG dump file. And so this is really cool because we have sort of infinite information about all our atoms. And so we could write coloring according to position in X, Y, or Z, forces in X, Y, and Z, their central symmetry, their energy, or the atomic stresses. So just take a minute to play with those. So if you color according to the Z position, you start to get this rainbow. You might need to play with the start and stop values. Ovito doesn't do a very good job of sort of automatically changing those. So you can get some sort of this color from top to bottom in Z. Not very interesting. Maybe the more interesting one is central symmetry. So if you go from 0 to 40 is a pretty good range on central symmetry. If you are very close to a perfect FCC crystal, your central symmetry parameter is going to be close to 0. If you're very far from a perfect FCC crystal, your central symmetry parameter is going to be very high, typically around 40 for the worst case. And so you can see at the beginning of the simulation, everybody's blue. In the middle, the wall atoms are sort of red and green and pink and purple because they don't have neighbors to give them the FCC symmetry. And you can also see around the crack tip, the central symmetry is much higher. So it gives you a local measure of order in your crystal, and it aligns with what one would exactly expect. Yeah.
By local order, by local order.
So the center symmetry parameter is a little complicated to explain. You can look up the documentation in labs and see how exactly it's computed. But basically what happens is that you have a bunch of atoms in your system, you tag an atom, let's tag this guy, and then you look at its nearest neighbors, and so you look up, right, down, left, in and out of the board, and you say, are those nearest neighbors very close to where I should expect them to live for a perfect FCC crystal, or are they not? And so if you have a defect, if you have a missing neighbor, you're going to get penalized for that, so your central symmetry parameter is going to be away from 0. Or if you're at the edge and you don't actually have any neighbors because you have free space out to your left, you're going to get penalization for that. And basically, you tag an atom, you superpose around the atom what you expect a perfect FCC crystal to look like, and you say, does the environment of the atom look like that, or does it look different? How close is that atom to living in a perfect FCC crystal? So of course, if you had a different crystal, BCC or an HCP or diamond, you could also compute central symmetry for those crystal architectures. Central symmetry. And so that was the variable we defined in our LAMP input file and stored in this thing called CSym. So it was the compute that we defined near the top of our input file. Okay, so what else can we color by that might be interesting? So how about the atom stress in the Z dimension? And so for every atom, we went in and we computed what's its local stress tensor, and it turned out the third component of the stress tensor is going to be the Z stress. So I'm trying to get a decent range. Okay, so let me show the movie. Okay, so I'm now going to show you a movie of some of the things I just discussed where this version of Avito is not playing nicely with the value that I wanted. But this movie actually pre-computes the stress range that provides a nice way of actually seeing that the stresses evolved at the crack tip are maximal. So let's watch the visualization movie. Okay, let's go. Okay, so we're launching Avito. We're opening up the CFG file. We're modifying our pipeline. So we're going to color code according to stress in Z dimension. That was the button I was missing. So if you click adjust range, it will automatically adjust the range for you. So in the small window, I couldn't access that button. Okay, and so then you can watch your system evolve, and you should see that at the moment the crack tip is propagating, your Z stresses are going to be maximal. And so you see lots of red atoms down here, and then the crack starts to move. And so we're seeing the stress field atom by atom. Let me pause it here. And so right here, we're seeing that at the crack tip, there's bright red atoms, and the crack is going to start propagating through the material. And the stress field is also sort of high at this corner, and at this bottom corner here. And as you move in time, it's going to see the crack propagate. So how can we make a picture? Let me hit the button on my right screen. Okay. All right, so now I've managed to adjust the range. The resolution of the screen is too small for a VSOP. Okay, so now you can move to the frame that you're interested in. So perhaps it's just when the crack starts to propagate. So maybe right here. There we go, adjust range. Okay, then say you're writing a paper or you're giving a presentation and you'd like to make a snapshot. So highlight the window you like, and so this three-dimensional perspective is the one I like, so I'm going to highlight it. So just click on it and it should turn to yellow border. And then go up here and you can render the active viewport. So you get a nice picture. And then you can save it to disk. And so then you now have a nice PNG file that you can put in your presentation. The other useful thing is to click on this button. This is going to be important in your project. And this will export your color map to a file because these atoms have been colored according to the color bar and the range that you specified. And so when you present this image, you would also like to present next to it a color bar, telling the reader exactly what these colors correspond to. So if you hit this button, you'll be able to dump the color bar. And you'll then be able to put those things in your presentation or your Word document and make a nice image. Okay. What else? Okay, so the last thing you can do is also make a movie. And so if you go up to the top here, if you click on Render, render the active viewport. So I want this 3D perspective. You may want one of the two-dimensional views. You can render the complete animation. You can specify the image size, etc., etc. You can save it to File. So you can choose a particular file to dump it to. Then I'm going to have to pull this over for a second so I can access the right button. Okay, and then if you click Render Active Viewport right at the top there, it will start doing the rendering for you. Okay, has everyone managed to do that? Yeah. So you need to click on the picture there. Yeah. So then you set it up, you pick complete animation, and you make all the changes you want, and then when you're done, you can choose the file you want to save it to, and then you just click Render Active Viewport. Yeah.
Okay, I don't like color modification, like color coding. I don't have the option for it.
Yeah. So let's. So what file have you loaded here? Okay. So that one is the one that only has atomic positions, and so we said we need to actually load the CFG files.
So this is the one here, the render.
Yeah, looks good. So then you can save that.
And once you save it, it saves it. Or
it will save it, I believe, as like a GIF. Basically, in that it's a bunch of images all stuck together that play as a movie.
Oh, okay.
So you have to open it in like a web browser or something in order to actually see the movie play. But yeah, in principle, it's a movie.
So the image.
It will be a sequence of images.
Oh. Okay.
Yeah. Yeah.
Thank you. Render.
Everyone else managed to render stills and a movie? So that is the default. LAMP likes to save stuff as sort of sequences of images. So if you see like GIFs or PNGs on the internet, which are basically just sequences of images stuck together, that is sort of the default, but you can, of course, make other things. So if you go down to choose how you want to save your image, you can save as type, whatever you like. So maybe MOV or MP4 is a more conventional movie format. So you can pick that. Call it My Movie, save it to the desktop, and then render the active viewport. So in this particular instance, the reason that I don't render them as MP4 is because I don't have the right codec. You may have the correct codec to do an MP4. So just whatever works, basically. So let me actually try MOV. Maybe that will work. Okay, so I can save it as an MOV file. Okay, then on my desktop, I have this movie, which I can just play in QuickTime or whatever movie software that you have. And so you could dump that into a PowerPoint presentation or whatever you care to do. Okay, has everyone successfully managed to visualize and render their simulation? Anyone still having trouble? Okay, terrific. And so I think we just have one slide left. Okay, and so this was my rendering, and so I'm writing my report for my class, and so I have the side view in X and Z, so I put some axes to show the reader this is the XZ view, this is the YZ view. I picked it just as the crack was starting to propagate. I colored according to the Z stress, and so the atomic stress in the Z direction, so the ZZ component of the stress tensor, and I dumped out my color bar, and I had specified the ranges of my color bar from -200 to 200 gigapascals. And so the viewer can immediately interpret the colors according to this color bar. So this is a very important slide because this is exactly what I want to see from you in your project. If you're missing the color bar, if you're missing labels, etc., it's not a complete sort of presentation because we can't really interpret what you're trying to show. And so this is sort of the level of presentation I hope you'll be able to generate. Pretty easy. Okay, so last slide. We propagated a crack in a particular plane of aluminum under a particular velocity, so under a particular strain field. So how might you extend this work if you're interested in studying different things? So maybe you want to change the crystal orientation. So instead of propagating the crack in the 100, maybe you want to propagate it in some other crystal direction. So maybe you think it will propagate more or less easily along a different dimension, a different direction, and that can actually inform you as to where you should expect to see your cracks given your crystal orientation. So that could be very interesting. Maybe you want to see how changing the crack size or geometry impacts how it propagates. So if you start with a smaller crack or a larger crack or one that's sort of imperfect, we had a very nice notch, but maybe you want to make something that's more ragged. How does that change things? And then finally, maybe you want to explore the effects of system size. So we saw in our plot, if I go back a couple of slides, of the stress as a function of strain, this was the critical stress at which we caused the crack to propagate. So maybe you think, actually, I don't really believe this because I think my system was too small. Maybe I want to look at bigger and bigger systems, which will give me better estimates for this. And once your result is no longer a function of system size, perhaps then you're content to say, this is my measured critical stress. So just some examples of some extensions about how you may take this further. So this one is sort of trivial. Trivial to do anyway, because we did that at the beginning of class. You changed your system size. This is also pretty trivial. So the way you set up your lattice, you tell LAMP to put it in a particular crystal orientation. That's quite easy to do. This just requires a little bit of understanding of how we specified the geometry of the system and the crack. But again, it's pretty easy to change the size of your crack. So if you're interested, these extensions are sort of pretty simple and fun things to do. Okay, so that is it for the walkthrough. And so it took a little longer than I expected, but it's 10 after. And so we can either terminate here, or if folks want to stick around and start working on the project, that's also fine. I'll certainly stick around until the end of class. And then we'll pick up on Tuesday. So next week is going to be the in-class sessions when we're actually working on our project together. But that is available for you immediately to start working on now. And it is due, I believe, the 23rd. So let's pull up the syllabus. Okay, so today is October 9. Next week, working on the LAMP project. Then we'll get into finite elements, and the quiz for LAMPs and the project for LAMPs is due on October 23rd. So you got plenty of time. Great, so that'll do it for today. Like I said, I'll stick around if folks want to do that, but absolutely free to go and enjoy the rain otherwise.